Hello all, this is ML Naruto. Welcome to my channel. So today I'm going to explain the three subtopics in support vector machines. The first one is what is meant by support vector machine and what are all the applications of support vector machines. And the third one is what is the relationship or what are the similarities between the support vector machine algorithm and the remaining other algorithms. So I'm going to explain all these three subtopics in this video now. So, but before deep diving into these actual topics, just look at this amazing quote from Naruto series. So the quote is, people say I'm a failure. I prove them wrong. So the meaning of this amazing quote is, no matter how you do or how you perform or what you do, people around you usually mock you down. So there is no need to take those words to the heart. Okay. Instead, you can just take those words as a challenge just to prove the people wrong. Why? Because if you take any words or if you take any of those words directly to your heart, then it may affect your mental health. So instead of that, just take those words as a kind of stepping stone. By using those words or by using those stepping stone, you can just move towards your success or your goal, just to prove the people that they are wrong. Okay, so we never accept the failure. The meaning of this ultimate summary of this quote is, we never accept failure. Instead, we can use that failure as an experience. We can count that as an experience and we can move forward towards our goal. So that's the meaning. So here, so now I'm gonna explain what is meant by a support vector machine right now. But before that, I want to share something with you. Okay, earlier we have already seen that we have some kind of feature space like this, and after that we have some kind of points like this, and we also have some other data points like this, and we need to separate these two categories of data using a hyperplane. Okay, sorry. And we need to separate these data using a hyperplane like this. Okay, so this hyperplane is nothing but this hyperplane is a natural classifier. Okay, this is a hyperplane which is nothing but a natural classifier. Okay, so the SVC is nothing but it's the more generalized form of the maximal margin hyperplane. Okay, SVC is nothing but more generalized form of maximal margin hyperplane. So using this SVC, what we have done earlier, we tried to separate the two categories of the data using a linear decision boundary. See this here, the hyperplane here is actually a linear one, right? It's a linear one. That is, whatever may be the case, we used to separate the data using this linear decision boundary. Okay, linear decision boundary. Why? Because I'm calling it as a linear decision boundary. Why? Because the shape of the hyperplane is nothing but the linear, that is, it's a straight line. So that's why I'm calling it as a linear. But we usually find some of the cases in our real practical world. We don't have the data which is present in this particular format. Okay, we have data which for which we require some non-linear decision boundaries too. What is meant by that? I'll explain. See here. See here, I'll explain you. For example, we have the data like this. Okay, and here we have some kind of data points like this. And also we have some other data points like this. And now here we have the continuation of the previous data points like this. Okay. So the entire data has been categorized into two categories. First one is the red category and the sorry. This is the red category. Okay. And this is the purple category. Okay. So this is the red category and this is the purple category. So whenever you have a data like this, so how can you separate these categories of the data using a hyperplane? Can you separate the categories of a data by drawing just simply a straight line? Can you do that? No. Why? Because see here, if you draw a straight line in between these two categories of data, we are actually having the same category of red points. We are actually having the same category in a single plane, right? This is a single plane. So this is not the correct kind of classification. Why? Because we are not actually classifying the data points correctly. Why? Because our data points are still left the other side of the hyperplane. So I mean, this should not be the case. Like all these data points should be present at this point, right? See, these data points should be present here, the left of the margin like this. Why? Because majority of the data points are here, red data points. And we need to have purple data points to the other side of the hyperplane like this here. Like what I'm saying is, if this is a hyperplane, all the red points should be lying here and all the purple points should be learning here. See, this is the correct classification and this can only be done using, I mean, this can be done using a straight line. That is nothing but a linear decision boundary. For the time saving purpose, I'm just calling it as a linear DB. That is nothing but the linear decision boundary. Okay. But here, when you use the linear decision boundary, it should not be the case. The classification is not so perfect. So how to proceed with this kind of problems? So there comes to our rescue. That's nothing but the support vector machine. That is the SVM. So how to do that? I'll explain now. So how to do that? I'll explain now. So for example, we have a case, like we have a scenario like this. So these are the data points, some red data points, and we also have some kind of purple data points here in between these data points. So here in this situation, we can't even separate the data. We can't even separate the data using a single straight line. That is a linear decision boundary. We can't even separate like this. Okay. So, and also we have some kind of scenarios like this. See here, where we have our data and here we have. See, the data is actually combined here. So the data is actually merged here. So for this kind of data, the linear decision boundary would not be sufficient. Why? Because we everybody knows that. I mean, if you draw any kind of linear decision boundary, will it be separating the two categories of the data? No. Why? Because still I have two categories of my data on my right side, and still I have two categories of my data on my left side. So this should not be the case. The case should be, the ideal case should be, if I have a hyperplane like this, then the ideal case should be all the red points should be lying one side of the hyperplane, and all the purple points are actually lying the other side of the hyperplane. So this should be the ideal case. But with the help of the linear decision boundary like this, we can't even do such kind of things. So what we can do? So we are actually in a need of this particular algorithm, that is nothing but the SVM. See here, the SVM. SVM is nothing but the support vector machine. SVM is nothing but support vector machine. And when you just remind for the linear regression part here, you can just remind about the linear regression part here. So what happens is, our linear regression, we already know how does a linear regression algorithm work, right? So linear regression, if I want to fit any kind of linear regression, what would be the assumption here? It should be a straight line, right? It should be the straight line. The x here and the y here, it should have some kind of linear relationship. Then only I can fit this particular straight line. See, okay. For example, if we have the non-linear kind of things, okay. For example, we have non-linear kind of things. Then can I fit this straight line for the data which is non-linear? No, I can't even fit. So in such cases, what happens? For example, if we have the non-linear data, so for this data, we can't fit linear regression. Okay, we can't even fit linear regression here. So what we can do is, we usually increase the feature space, right? We usually increase the feature space. Feature space, what is meant by the feature space? Feature space is nothing but this one, right? This x-axis and the y-axis is nothing but our features. So we will extend the feature space. That is, we can extend multiple features here. So how to do that? We can do this. I mean, we can increase the feature space using what functions? Using the functions of the input variables. Using the functions of the input variables. Functions of the input variables, what does this mean actually? Those are nothing but the cubic, the quadratic functions. I'll explain you what does this mean by cubic and quadratic. When it comes to the linear regression part, I'll explain you in that video, because that would be a lengthy topic. So for now, just remind this word, that is, we usually we want to fit this particular algorithm to our data. So for a linear type of data, we can fit this, but for a non-linear type of data, we can't even fit the linear regression. So if we want to fit the linear regression for a non-linear kind of data, so what happens? We need to increase the feature space, right? See here, we need to increase the feature space here. How to do this? Using functions of the input variables. So what is meant by these functions of the input variables? Nothing but the cubic and quadratic, right? Cubic is nothing but, you know this, right? Cubic, quadratic. So all these are the cubic and quadratic are nothing but the input functions of the input variables. So I'll explain you whenever I explain the linear regression topic. I'll explain. Okay. So for now, just understand this. So linear regression algorithm is usually fit using this cubic and quadratic functions, right? So in this in SVM also, in SVM also, in SVM also, we increase the feature space using the same functions, these functions cubic and using cubic and quadratic functions. So what is the name for which we call cubic and quadratic functions? So the name here is, the name for the cubic and quadratic is nothing but the polynomial. Polynomial. So the name here is polynomial function, right? So why we are actually using this features? I mean, why we are actually maximizing this feature space? Why we are actually increasing the feature space using cubic and quadratic functions, that is polynomial functions? Why we are actually doing this? Why? Because we need to fit our algorithm. We need to fit our algorithm for the non-linear kind of things, right? See here. If you didn't understand, just look at here. What we have already explained. See here. We have some kind of scenarios, like these are the non-linear kind of scenarios, right? These are the non-linear things. So for this kind of scenarios, we need to maximize our feature space. Okay. So for that purpose, what we are actually doing is, maximize our feature space. So for that purpose, we are actually maximizing our feature space using cubic and quadratic functions. Those are nothing but the polynomial functions. Okay. So how to do that? Now just look at here. But here we have a condition, like we do this instead of using p features, that is p number of features, we use 2p features. So what does this 2p features? I'll explain. Don't worry. So for example, if I have the p features, okay, p features. So what does this mean? P features are nothing but x1, x2, x3, and so on, xp. These are the p features, right? See here, these are the p features. So now I want to use these 2p features. What is this 2p features means? x1, x1 square, x2, x2 square, and so on, xp, xp square. Okay, these are nothing but the 2p features. Why we are actually using 2p features instead of p features? Why? Because we need to fit SVM for our data. For which data? That is non-linear kind of data. Okay. So the whole purpose is very, very, very simple. Why? Because see, we having some kind of, I'll explain. See, we having some kind of non-linear data. Okay. So for which SVC, that is support vector classifier, won't work. Okay, this won't work. So what we need to use? We need to use SVM. This will work. So how to make SVM work for this non-linear condition? It's very simple. Like in the same case of the linear regression. See here, in the linear regression itself, we usually increase the feature space. Okay, feature space. Why we are actually increasing the feature space? Why? Because we need to fit our linear regression to the non-linear kind of data. So how to increase this? How to maximize this feature space using the polynomial functions, that is cubic or quadratic. So the agenda is very clear here. See, very clear. In the same way, we are also actually using our SVM, support vector machine, to fit for the nonlinear data. So if I want to fit this SVM to the nonlinear data, what we need to do? We need to maximize our feature space here, the above here. Maximize our feature space using what? Using the quadratic function. The quadratic function is nothing but the polynomial function, right? Polynomial functions. So how to do that? See here. If we are actually using p features, that is x1, x2, x3, and so on xp, we will use, instead of p features, we use 2p features. That is x1, x1 square, x2, x2 square, x3, x3 square, and so on xp, xp square. So these will be used instead of that. Okay. So here, okay. So here actually, earlier we have already said, earlier we have already looked here, that is, we have a optimization problem, right? We have an optimization problem. Okay. What does this mean? That is, we need to maximize, beta naught, beta 1, and so on, comma, beta p, comma, epsilon 1, comma, and so on, epsilon n. Okay. Then this will impact sigma j is equal to 1 to p beta j square is equal to 1, and then y of beta naught plus beta 1 x 1 plus beta 2 x 2 plus, and so on, plus beta p x p should be greater than or equal to m 1 minus epsilon I. So here we have a condition called epsilon I should be greater than or equal to 0 and I equal to 1 to n epsilon I. This should be less than or equal to c. C is nothing but the tuning parameter, which I have already explained in the support vector machine SVM part 2 video. Those who haven't watched the previous two parts, I'm just keeping the link of that video here in the I button itself, so you can go there and watch it. Okay. So this is nothing but the optimization problem. Okay. This is the optimization problem. See here. This is nothing but the optimization problem. Okay. And after using this, see here. After using 2p features, after using 2p features, this optimization problem becomes like this. See, Here also we need to maximize, right? Maximize the margin. That is beta naught plus beta 1, beta 1 1, right? Beta 1 2 and so on, comma beta p1, sorry, so beta p2, okay, and epsilon 1 and so on, comma epsilon n. So this would be the same, but this impact y of beta naught plus sigma j equal to 1 to p beta j 1 into xi j plus sigma j equal to 1 to p again beta j2 into xij square. Okay, so this should be greater than or equal to m of 1 minus epsilon I. One minus epsilon I. Okay, what happens here? We have a condition similar to the earlier one. I is equal to 1 to n. Epsilon I is less than or equal to the same condition. Epsilon I should be greater than or equal to 0 and sigma epsilon equal to I is equal to 1 to n. Epsilon I should be less than or equal to c. Okay, and also additionally we have another condition, that is sigma j equal to 1 to p sigma k is equal to 1 to 2 beta j into k square is equal to 1. So this would be the value of beta jk square is equal to 1. So this would be the condition. So did you get some kind of change here? See here, earlier okay, see here earlier we have this kind of optimization problem, which is nothing but we need to maximize this m, and here we have the parameters beta naught, beta 1 and so on, beta p. Okay, and we have the slack variables. If you don't understand, I mean if you didn't understand what is meant by the slack variables, just go here in the I button. Here I am explaining, here I have already put the previous two parts of this SVM, so just refer to the second part here. There I have clearly explained what is meant by epsilon. Okay, this is the epsilon here. So for that I have already explained. So epsilon 1, epsilon 2 and so on, epsilon n are nothing but the slack variables. So these are the parameters. Okay, and here we have the effect here, that is beta j square is equal to 1. Okay, and here we have the function, that is y of beta naught plus beta 1 x1 plus beta 2 x2 plus and so on beta p xp. The value of a function should be the value of a model should be greater than or equal to m of 1 minus epsilon I. And here we have a condition for this epsilon value, that is epsilon I should be greater than or equal to 0 and it should be less than or equal to c. So earlier this was the optimization problem, but after we use 2p features, this optimization problem becomes like this. Here, see here, our parameters are actually like this: beta naught, beta 1 1, beta 1 2, beta p1, beta p2, like this. Okay, these are our parameters. And here when you look at here, these are the same for the slack variables, right? These are also the same here in the previous case, and here also the same in the uh, I mean in this case. Okay, now this is our model y of beta naught plus square sigma j is equal to 1 to p beta j1 xij plus sigma j is equal to 1 to p beta j2 xi j whole square xij square should be greater than or equal to m of 1 minus epsilon I. Okay, the whole value of this function should be greater than this function, that is greater than m of I 1 minus ei. So earlier we have this particular function here, but now our function is actually changing. Why? Because our parameters have already changed. Okay, why? Because we have used these 2p features here instead of p. Okay, earlier it was p features. Earlier, okay, now we have changed it to 2p features. So due to that change, our parameters have been changed, so that which results in our model also changed. Okay, but the condition for these slack variables remained the same. See here, epsilon I is greater than or equal to 0, the same here, and epsilon I should be less than or equal to c, which is the same in this previous case also. But additionally we have got another condition, which is nothing but beta jk square should be 1, right? So what is this condition? This condition is nothing but the same condition as like this, right? See here, beta j square is equal to 1. Okay, here the here the how can I say? Here the input variables are actually linear, right? Here the input variables are actually linear. So for that reason, we are actually treating beta j square equal to 1. But here our our linear variable, but our here our uh, input variables are actually not linear. These are actually cubic. Okay, these are actually cubic or quadratic, nothing but the polynomial. Okay, earlier our features are our variables are earlier our variables are linear. Okay, but here now our variables are quadratic or cubic, that is nothing but the polynomial. That's nothing but the polynomial, right? So for that reason, we are actually having beta jk. Okay, beta jk square is equal to 1. This value should be 1. So this is of the same kind as this, right? See here, this is here also we have beta j square is equal to 1. Here also we are having beta jk square is equal to 1. The difference is here we have additional term called k. Here we don't have that k term. Why? Because we are actually converted the p features to 2p features, which are nothing but the polynomial features here. Okay. So for that reason, we are actually seeing. So what happens if we calculate this term? Okay, we have calculated this entire expression, and what happens? So we have calculated the entire expression here. Then what happens? I need to know. So what happens? This equation, okay, this equation can form a non-linear decision boundary. Okay, this entire expression can form a non-linear decision boundary with which we can classify the data points. Right. So did you understand earlier? See here. See here. Did you understand this? Earlier, this was the scene, right? Earlier, we have the separable, easily separable classes, but now we have the data in this format. So we can't even separate using a simple straight line. So for that purpose, we need some kind of extraordinary, which is nothing but the support vector machine. So for that reason, we are actually calculating that particular expression, which in turn gives us which in turn see here, which in turn give, if we calculate this entire expression, see, if we calculate this entire expression, what happens? We can this entire expression can form a non-linear decision boundary with which we can classify the data points correctly. Okay. So how to do that? I'll explain now. See, see, the theoretically, if we have the, okay, if we have maximized, okay, if we have already maximized feature space, okay, we have already maximized this feature space. Okay, I'll explain. Okay, we have already maximized this feature space. So what happens if we maximize this feature space? We get some non-linear. See, I'm saying here, if we maximize this feature space, okay, usually what we get is we get a decision, we get a linear decision boundary. Okay, we get a linear decision boundary. Okay, this is, see here, see the term here, observe the term. It's a linear decision boundary. Usually, this is the case usually. Okay, but what happens is, but in practical, okay, but in practical case, but in practical case, when we maximize, when we maximize the feature space, what happens when we maximize the feature space? We will get, when we maximize the feature space, what we will get? We will get a decision boundary. And it has the form, okay, it will be, in the form of q of x is equal to 0. Okay, so here what is meant by this q here? Since what is meant by this q? Q is nothing but a quadratic polynomial. Okay, q is nothing but a quadratic polynomial. So we everybody knows that for any polynomial, quadratic polynomial, it has the solutions as non-linear, right? So polynomial is nothing but it has the solutions like for the q is nothing but for any quadratic polynomial we have the solutions which are non-linear. See here, this term is very important here. Why? Because I'll explain. See, usually this is the case. This is the general case, general scenario. So this would be the general scenario. When we try to maximize the feature space, what we will get is we will get a linear decision boundary, and this is nothing but this is a general scenario. I mean, usually we need to get this, but in practical, if we maximize the feature space in practical, we will get a decision boundary which will be in the form of a q of x is equal to 0. Here q is nothing but a quadratic polynomial function. So for any quadratic polynomial, we have the solutions which are a non-linear form. So ultimately, this decision boundary is actually a non-linear decision boundary. Did you get the point? Right? I'll explain, no worries. See here, earlier we have the maximum, we have already maximized the feature space. That is, we have increased this feature space. Then we are getting a, simply we are getting a linear decision boundary. This would be the general case scenario. But in reality, what is happening is, when we maximize the feature space, we are getting a decision boundary, and that decision boundary is of the form q of x is equal to 0. The q is nothing but here quadratic polynomial. So that for any quadratic polynomial, we have the solutions which are nothing but the non-linear. So for any quadratic polynomial, the solutions will be in the form of non-linear, right? We won't be having any kind of like this situation. I mean, we don't have any kind of this particular cases here. We will be having these particular cases here. I mean, the hyperplane should be the non-linear here, right? So this would be the case. And how to maximize this feature space? Did you ever think how to do that? We have already maximized the feature space, okay, but how to do that? I'll explain now. How to maximize? How to maximize? Yes. I'll explain. How to maximize the feature space? How to do that? How to do that? So for that purpose, for that purpose, we use high order polynomial functions. High order polynomial functions, right? We can also use interaction functions. Don't worry, I'll explain each of these topics. So first let me write. So we can maximize the feature space using these two. Like we can use the higher order polynomial functions here, and we can also use interaction functions here, right? So what is meant by interaction function? Interaction function is nothing but it's very simple. Like see, interaction function is that would have some kind of shape like this, xj and xj dash. So it will have the shape like this. But here where j is not equal to j dash, so this would be the shape, and this would be the condition for interaction functions. Okay. But what I have said, we usually use higher order polynomial functions. Okay. And also, what we can do? We can also use other functions. Okay. We can also use other functions to do this. That is, if we want to maximize the feature space, we can use higher order polynomial functions, or we can use the interaction functions. We can also use other functions. Okay. But we should be very careful. We should be very, very, very careful. But we need to be little careful. Why? Because we may end up forming huge number of features. So what I'm saying, did you get that? So there are so many ways. Okay. So if we are not actually careful in picking up these methods, so what happens is we may end up creating huge number of variables, huge number of features. Okay. We will end up huge number of features. So we need to be very careful in picking any of these methods. Okay. So see here, first of all, if we want to maximize the feature space, what is the approach? We can use higher order polynomial functions. We can also use this interaction functions also. We can also use other functions also. Okay, but we have our SVM. We have the SVM classifier. We have the SVM, support vector machine algorithm. This is not a class. Actually, this is a support vector machine. So this our algorithm will do this kind of job. Okay, will do this. Why I am saying like this? Why? Because see here what I have said. If we need to be very little careful. Why? Because if we are not actually careful in picking these methods, then what happens is we will end up forming huge number of features, right? So to avoid that kind of situation, see, to avoid this, we use support vector machine. Support vector machine, which is actually it's a computationally efficient. It's computationally very, very, very efficient. Why? Because see here, if we are not actually careful about picking those methods, we may end up forming huge number of features, and that would be a huge mess, right? But here our support vector machine will usually be little careful, and it will do this kind of job very efficiently. By this we are actually performing the tasks which is computationally efficient. Okay, we won't take much time by performing this. So now, did you understand why we use this support vector machine? So for this purpose, we use support vector machine. No worries. I'll at the end of the video, I will try to recap all the things which we have already covered. Okay. So, but this will be the reason why we use the support vector machine. So now you got the reason to use the support vector machine, and now you need to know now you need to know why do we what is mean by support vector machine actually, right? Okay, so now I'm going to explain what is mean by support vector machine. support vector Support vector machine. Okay, so now I'll explain. So support vector machine is nothing but it's an extension. Okay, it's an extension of support vector classifier, which we have already discussed in our support vector machine part 2 video. Okay, so those who haven't those who haven't watched this particular support vector classifier video, I'll suggest them to watch this particular SVM part 2 video. In that video, I have already explained what is meant by support vector classifier. Okay, so support vector classifier is usually used to perform only the linear kind of cases here. See, we have some kind of data points here. We have data points. We can only perform no matter whatever may be the how clumsy the data is. But here we will only use this particular support vector classifier with which we can allow some kind of we are actually forming some. I'll explain. See here, actually, I'm having some kind of data points. Okay, here also I'm having some kind of data points, and now I have some other data points like this. So in order to separate this particular thing, what our support vector classifier will do is usually it will forms a some kind of margin here. Okay, so it allows some kind of data points to be placed on the wrong side of the hyperplane also. Okay, it will usually classify some kind of hyperplane, some kind of data points to place on the wrong side of the hyperplane. But see here, when you use support vector classifier, the efficiency would not be the same as if we use the support vector machine, right? Why? Because see, this support vector classifier is only suitable for specific kind of data. For example, if we have some kind of data like this, and we already have some kind of data like this, okay, it will usually forms a hyperplane here, then it will have the margin here, then it will have the margin here. Then if we have some kind of data points like these purple data points, we are actually having the data points here uh, inside this particular side, then this svc here, svc is useful. Okay, but in such cases, like I have already said, right? See, in such cases, here the data has already been merged, right? So in such cases, it is almost difficult to use support vector classifier. So what we are actually doing is we are actually using the extension of the support vector classifier, which is nothing but the support vector machine. Okay, right? So I'm just now erasing all these things. So what happens if we use this support vector classifier? What happens if we use this support vector machine here, right? What happens? I mean, we are actually what is meant by support vector machine? Support vector machine is nothing but it's an extension of the support vector classifier. Okay. So how do we create a support vector machine? We create we create we create an SVM after maximizing our feature space, right? After maximizing our feature space, we can create our SVM. How to maximize this feature space? For that we can use we use some kernels. Okay, kernels. So these are the kernels here. So using these kernels, we can maximize our feature space here, and then we can create SVM. Okay. And what is the need for the creation of this SVM? Nothing but just now I have already told, right? Just now I have already told to separate the linear kind of cases. That is, our decision boundary should be like this, okay, or some other thing, any of the thing like this, no matter whatever may be the linear boundaries. Why? Because this is a kind of scenario where we have our data as a linear kind of non-linear kind of things. Like see here. So in such cases, we use SVM to separate this kind of data. Okay, that's the reason why we actually want to create SVM, right? So for that purpose, we use kernels here. So what is meant by kernel and what is the functioning of the support vector machine? I'll explain in detail, great detail. So for now, just focus on here. So we have the optimization problem, right? Earlier we have already seen the optimization problem. So if you want, see here, when you look at here, this is our optimizational problem, right? This is our optimization problem. What is that optimization problem? Beta 1, beta p, and so on. This entire thing is nothing but the optimization problem, right? So for this optimization problem, if we want to solve this optimization problem, the solution is nothing but the inner products of the data points. So I'm going to explain what is meant by this inner products of the data points. I'll explain. Hello. So now I'll explain. See here, we have already seen the optimization problem, right? We have seen previously what is meant by this optimization problem. Okay. So if we want to solve this optimization problem, our solution of this solution of this problem is nothing but the inner products, right? Inner product of the data points. So what does mean by that? That is, for example, I have vectors a comma b, and the inner product of these vectors is nothing but sigma I equal to 1 to r ai comma ai into bi. So this would be my inner products of the vectors a comma b. Okay. And if I want to apply this particular kind of form to our optimization problem, what would be the case? The case is xi comma xi dash. Okay. Then what would be the form here? Sigma j is equal to 1 to p, then xij into xij dash. Okay. So here this, and here I want to mention one thing, like here, since here a comma b are the vectors, here a comma b are the vectors, and here xij, sorry, xi comma xi dash are the vectors here. Okay. So how can we write our model here? Model is nothing but f of x, right? So f of x is nothing but our model. So how can we write this f of x here? Beta naught plus, earlier we have beta naught plus beta 1 x1 plus and so on plus beta p xp, right? So this would be the form earlier. But now what we can write is f of x is equal to beta naught plus sigma I is equal to 1 to n into, alpha I. We can mention this particular inner product here. That is x comma xi. We can mention this. Okay. What is this x comma xi? Nothing but the x is nothing but a, see here, x is nothing but a new data point, and xi is nothing but the all the remaining data points. Okay. So we, instead of representing beta 1 x1 plus beta 2 x2 plus beta p xp and so on, we can use some kind of short form like this, alpha I into x comma xi. So these are our variables, and this is our parameters, right? This is the representation of our slope. Okay, beta 1, beta 2 and so on. All these betas are nothing but the slope here, right? So this is nothing but the intercept. Okay, see, this is the, this is the intercept. Okay, and beta 1 and beta 2 and beta p, all these are nothing but the slopes here. Okay, so here these are nothing but the, this is the representation of the slope, and these are the variables here, right? And this is the intercept here. So we can modify the earlier equation for this optimization problem as like this: beta naught plus sigma I equal to 1 to n alpha I into this x comma xi. So what is this x comma xi? These are the variables, and we have placed some kind of the inside some kind of brackets, right? Less than or equal to brackets. So what is this entire thing? This entire thing is nothing but, inner product of the data points. Okay, so this entire thing is nothing but the inner product of the data points. So that's the thing here. So here, let's say we have, so we have from the above equation, what can we derive? We have n number of parameters here. See here, from the above entire expression we can derive, we have n number of parameters. That is nothing but I is equal to 1, 2, 3 and so on n. So this is the representation of the slopes alpha. Okay, so we have such alphas, we have up to n. Okay, so we have n parameters. So that is nothing but, that implies alpha I is equal to alpha I, and where I is equal to nothing but 1 comma 2 comma and so on comma n. Okay, that is the meaning of this is 1 per each training data point. Okay, these are nothing but the representation of our training data points. Okay, so if we want to calculate the x, okay, now we want to calculate the f of x, right? So if we want to calculate the f of x, then what happens? First of all, we need to calculate first we need to calculate the inner product. Calculate the inner product between x and xi. So what is this inner product between x and xi? X is nothing but here, x is equal to new data point. Okay, xi is nothing but remaining all rest of all the data points. So xi is nothing but rest of all the data points, and new data x is nothing but the new data point. Okay. So what happens is, first of all, we need to calculate the inner product between this new data point to the each of the rest of the rest of all the data points. Right? I'll explain here. For example, I have the new data point here. Okay, and here I have one existing data point. This is our old data point. That is nothing but our training data point. We have x2, we have x3, and so on. We have xi. Okay, so this is our new data point. Let's say star. Okay, I need to calculate the inner product between x and x1, x and x2, x and x3, and so on. Okay, x and xi. Okay, so I need to calculate this thing. These are nothing but the inner product. This is nothing but the inner product. How can we represent this? We can represent this as like this: x comma xi. So this is the test data point. Okay, and this xi is nothing but the each of the remaining training data points. Okay, so this is it. And here I have some kind of condition, right? So I'll explain that. Here I have some kind of condition. For example, here, let's say if if our x, okay, that is if our new data point is a support vector. If our new data point is a support vector. So what is meant by support vector? That is nothing but support vector is nothing but we have a hyperplane here, and we have some margin here. We also have some margin here, and here on exactly on the margin we have some kind of data points. Okay, there may be any number of data points, but that would be exactly on the margin itself. So these data points are nothing but the support vectors. Okay, so here we have a condition that is nothing but if our new data point is a support vector, then what happens? If our new data point is a support vector, then what happens? Alpha I is not equal to 0. Okay, that's the condition here. If x is not a support vector, if x is not a support vector, then what would be the condition here? Alpha I is equal to 0. This would be the condition here, right? So did you understand? So this alpha term is actually depending Okay, this alpha term, I'll explain. See here, this alpha term is actually depending on this particular new data point, whether if it is a support vector or not. Okay, so indirectly this alpha term is actually depending on the support vector term. Okay, see here, this alpha term is also actually depending upon the support vector term. So how can we write this expression again? F of x, how can we write that expression? See, we can write this, therefore we can write f of x is equal to beta naught plus sigma I belongs to S alpha I x comma xi. I can write this. Why? Because see earlier what I have written. See earlier I have written in this place I is equal to 1 to n. Okay. But here what I am saying is this alpha value is actually depending upon this x value, whether if it is a support vector or not. So the quality of being this x is a support vector, or if it is not a support vector, alpha value is actually depending upon this quality. So what I'm saying is I am wrapping all my I values that belongs to S. S is nothing but a support vector. Okay. So I'm writing here. Uh, so S is nothing but it's a collection of indices of the support vectors. Okay, so now did you get the entire thing? See here what I have explained. Did you get this entire thing? See, did you get this? For if we want to create a support vector machine using kernels, so what we need to do is we need to maximize the feature space, right? We need to maximize the feature space. See here, we need to maximize the feature space. For that purpose, what we can use is we usually use instead of using the p features, we will use 2p features. Okay, so if after doing this 2p features, what we are actually getting is the solution for this optimization problem is nothing but the inner product. Okay, inner product is nothing but the product between a new data point and all the remaining existing data points. Okay, so this would be the formula. This would be the ideal formula, and this would be the application of the formula to our optimization problem. So then xi comma xi dash are nothing but our vectors. Why? Because a comma b are here vectors. So that's why xi comma xi dash are nothing but our vectors. And here this is the earlier f of x. Okay, this is the earlier f of x. And now after using this inner product here, we can directly substitute this inner product in between these other parameters. So that's why then xi comma xi dash will be the variables. This would be the slope, this would be the intercept. And now I have just explained the entire expression meaning. See, we have n parameters. Nothing but alpha has some n number of parameters, that is I equal to 1, 2, and so on n. So 1 for each training data point. So f of x is nothing but if we want to calculate the f of x, then what can we calculate? How to calculate this? So first of all, if we want to calculate the f of x, first of all we need to compute the inner product between x comma xi. Okay, so I have explained what is meant by inner product. The inner product is nothing but this the product between x and x1, x and x2, x and x3, and so on x and xn. Okay, inner product is nothing but this is the test data. This is the each of the remaining data points. Okay, and here we have a condition. If our new data point is a support vector, then alpha I would be not equal to 0. If xi, I mean, if our new data point is not a support vector, then what happens? alpha I will be 0, equal to 0. So I can directly say this alpha value is actually depending upon the support vectors. So what happens is we can write this equation as f of x equal to beta naught plus sigma I belongs to s. S is nothing but the collection of indices of the support vectors. Okay, and the rest of the formula is same as it is. Okay, so this would be the case. Okay, so this would be the case here. Now what we can do is, see, when you compare the other, when you compare the earlier equation like f of x equal to beta naught plus beta 1 x1 plus beta 2 x2 plus and so on plus beta p xp, we have so many kind of terms, right? But now when you compare this equation, that is beta naught plus sigma I belongs to s and alpha I x comma xi, when you compare these two equations, this equation has very less terms. Okay, very less number of terms. See here, we have 1, 2, 3, and so on, so many terms, right? See, but when you compare this equation with this equation, we have the terms are already been reduced. Okay, so that's it. And so, and we want to estimate this parameter alpha I comma beta naught. Okay, then how to do that? We want to estimate parameters, that is alpha I comma beta naught. Then how to do that? So for that we calculate the inner product. So what is meant by the inner product here? I have already explained. So what is meant by this inner product here? Inner product is nothing but see here. Inner product is usually represented using this kind of notation, n2. Okay, so this is nothing but the inner product x comma xi between all pairs of data points, right? So what does the meaning of this all pairs of data points? I have already explained, right? Inner product is nothing but x comma x1, x comma x2, x comma x3, and so on, x comma xi. So this is nothing but the meaning of this all pairs of inner product. Okay. So what does this notation gives us? N2, this is nothing but the representation of inner product, and this would give us, it gives number of pairs among set of n items. See, let's see here, x1, x2, x3, and so on, xi. These are nothing but the n items here. Okay, these are nothing but the n items here. But when you see the pairs here, x comma x1 is a pair, right? This is a pair, and this is a pair. This is a pair. So such pairs, how many do we have? How many pairs do we have in our inner product term? Is actually known by this particular notation n2. Okay, this will tells us the number of pairs actually having among the set of our n items. Okay, so how many such pairs? See here, this is one pair, right? This is one pair, this is one pair. So such pairs, how many do we have in our inner product, is actually known by this particular term n2. Okay. So what happens is here we now replace inner product into support vector classifier. Okay, we have support vector classifier, and inside that support vector classifier we have some kind of inner product, right? So we replace that support vector classifier equation with what? Nothing but k of xi comma xi dash. Got it? So here k is nothing but the kernel. The kernel. What is a kernel? It's a function which measures the similarity. It measures the similarity between two data points. Okay, that is, I can write here k of xi comma xi dash is equal to sigma j equal to 1 to p xij into xi dash j dash. So this would be the formula for k of xi comma xi dash. Xi comma xi dash, k of xi comma xi dash is nothing but the inner product here, right? This is the inner product here. So, but if you can clearly observe the definition of this equation, see here, what is the definition of the kernel? It's a function which measures the similarity between the two data points. See here, it's actually measuring the data points between the two data points. Okay, so for that purpose we are actually using the kernel function, right? So if you use this particular equation if you keep this particular inner product equation inside the, I'll explain. If you keep this k of xi comma xi dash is equal to sigma j is equal to 1 to p xi j into xi dash j dash in support vector classifier equation, what happens? Oh, not actually support vector classifier equation. Why? Because we have already modified this equation, right? So I'll explain. See here. See, earlier we have the kernel function like xi comma xi dash, right? So this is actually measuring the distance between the similarity between the two data points xi comma xj. Okay. See here, replace the inner product in SPC equation with this. Okay. Earlier we have the inner product, that is nothing but alpha comma alpha of, I'll write here. Earlier we have the expression like alpha of xi comma xi dash, right? So if you replace this entire expression with this k of xi comma xi dash, then that would gives us the support vector classifier again. Okay. So what I'm trying to say is, if you keep this equation, sorry, See, what I'm trying to say is this k of xi comma xi dash will give us the support vector classifier again. So we will get the support vector classifier now. Why? Because we have replaced the inner product with the term k of xi comma xi dash. Okay. So this expression, right now, this equation, which equation? This equation is what? What is this equation? That's nothing but this equation means this k of xi comma xi dash. Okay. This equation is known as linear kernel. It is known as the linear kernel. Okay. Why it is known as linear kernel? Because support vector classifier is actually linear in features, right? The features would definitely have the linear kind of decision boundaries here. So that's why we are actually calling this particular equation as linear kernel, right? What does this linear kernel do? This linear kernel will actually measures the similarity between the two data points. Okay. It measures similarity between two data points using what? How does it measure? Using Pearson standard correlation. Using Pearson correlation coefficient, it will usually measures the similarity between the two data points. Okay. And we can also write this equation as, let's say, k of xi comma xi dash, sorry, xi dash here is equal to 1 plus sigma j equal to 1 to p xij into xi dash j dash to the power of d. Okay. So here, this entire equation, so here, this equation is called as polynomial kernel. See, earlier we have a different, see, this is the difference, right? This is nothing but the linear kernel. Why? Because it's only having the power 1, right? See, if we have nothing here, sorry, not here. Let's see. See here. Actually, it doesn't have anything. That's nothing but it's the power 1. It's actually rising to the power 1, right? So if it is actually rising to the power 1, then we can call it as a linear kernel, right? But here, that's not the scenario. That's not the scenario here. Why? Because here we can have anything as a power, whatever you want. Like, for example, if we have the d value, maybe it's actually varying. The d value can be 1 or 2 or 3 and so on. So here the d value is very critical. Okay, and the d is actually a positive integer. Okay, it should not be negative. The d is actually a positive integer. So due to that reason, due to this particular d value, we are actually calling this equation as a polynomial kernel. Kernel. Okay, polynomial kernel. And if you want me to define what is a support vector, if you want me to define, see here. If you want me to define what is meant by support vector classifier, I can define support vector classifier is a support vector classifier is a what is this? Polynomial. It's a polynomial kernel with d is exactly equal to 1. Okay, so I can write here. So what does that mean? That means k of xi comma xi dash is equal to k is equal to p and xi comma j into xi comma j dash, the whole to the power of d is equal to, here in place of d is equal to, here we have 1. Okay, when the d is 1, we can call this entire expression as a linear kernel. If we are actually using the linear kernel, then that's nothing but called as the support vector classifier here. Okay, right. But what if the d is actually greater than 1? Okay, I'll explain here. If the d is greater than 1, then we can get flexible non-linear boundary than support vector classifier. Right, did you get the point? See here, d is equal to 1, so that's why we are actually getting the support vector classifier. But what if d is greater than 1? Then we get a see here, when d is equal to 1, we will get a decision boundary which is linear, like this. Okay, we will get a decision boundary which is linear, that is a straight line. But here, when d is actually greater than 1, then we may get any of the shape, like we will get like this. Okay, this is a decision boundary which is actually separating a few data points here. See, it's actually separating few data points here, and it's actually separating the few data points here. Okay, see, likewise we will get the non-linear boundary with the help of this parameter d. D is nothing but the it's a polynomial kernel, right? So what happens when we get the nonlinear decision boundary? So what does that mean? Okay, we are getting the nonlinear decision boundary. So with which what we can actually do? Then we can use this nonlinear boundary to wider range of problems, right? nonlinear boundary, nonlinear decision boundary to wider range of problems. Why? Because earlier we can't even use the support vector classifier for the nonlinear cases, but here we can use this nonlinear boundary to any of the cases. Why? Because most of the problems we face in our real world are actually belong to this particular category, that is nonlinear category, right? And also I want to say something like when support vector classifier is combined with the non-linear kernel. Okay, non-linear kernel. Kernel is nothing but the decision boundary here. Okay, kernel. Then what is this non-linear kernel? Non-linear kernel is nothing but the polynomial kernel. So I'm saying that when we when the support vector classifier is actually combined with the polynomial kernel, then what happens is then we get support vector machine. Okay, so mathematically we can write this entire definition as, we can write this entire statement as like this: f of x is equal to beta naught plus sigma I belongs to s into alpha I into k of x comma xi. So this would be the case for SVM, that is support vector machine. Mathematically this would be the condition for the support vector machine. Okay, and I want to remind you one thing, like see, when d is equal to exactly 1, then what happens? SVM will become as support vector classifier. Okay, why? Because see, right, I have already explained it. You know this. See here. So this would be our ideal equation, right? No, not this one. See, where is it? Yeah, this would. See here, this would be our polynomial kernel, right? So if we combine the support vector classifier, then we are actually getting the support vector machine. Okay, but just see here, but just focus here. What is this 1 plus, and so what is this 1 plus sigma j equal to 1 to p xij into xi dash j dash? These are nothing but the inner product of the data points, right? We can also write this as beta naught plus sigma I. See, I can also write this entire expression as, I can also write this entire expression as like this. Got it? Xij into xij dash. So what is, how can we also write this entire expression as? We can also write this entire expression as like this: beta naught plus sigma I belongs to s alpha I into x comma xi. So this would be our equation for the SVM. Okay, this would be the equation. Just remind one simple point here, which is nothing but if d, see here, just observe the formula here. Okay, it will have some kind of formula like the whole to the power of d, right? Will have some kind of whole to the power of d formula, but I'm not writing here. Why? Because this is the formula for the support vector machine. Okay, so when d is equal to 1, support vector machine will become support vector classifier. Okay, when d is greater than 1, then what happens? Support vector classifier will become support vector machine. Not actually, this is not the correct term. I think it's not the. So it's actually behave. Okay, we can write it as behave. See, actually, this is a support vector machine. Okay, when d is equal to 1, then it will behave as a support vector classifier, right? But when d is greater than 1, then this support vector classifier will usually will behave like support vector machine. Got it? So that would be the case here. And now, and now I will explain something. See here, uh, if you want to maximize the feature space, we can have many functions for that. We have many functions for that. Okay, one such function is polynomial function. Got it? So if we calculate this polynomial function, we inside this expression we have got one kernel, which is nothing but the polynomial kernel, right? Earlier we have seen polynomial kernel. So this polynomial kernel is actually one of many kernels, right? We have many other kernels. Another kernel we have is nothing but the radial kernel also. We have the radial kernel. This is the polynomial kernel. It's okay, but another kernel we have, that is radial kernel. Okay, so what is the radial kernel mathematically? Mathematically, it's nothing but see, it's the same. K of xi comma xi dash is equal to exponential of minus gamma into sigma j equal to 1 to p xij minus xij whole square. So this would be my formula for the radial kernel. Got it? So here, what is the meaning of this gamma? Gamma is nothing but a positive integer, right? So here, it's a positive integer. And if you want me to explain how does this radial kernel work, then I'll explain. How does a radial kernel actually work? I'm going to explain. See here, see, if we have a new data point, that is nothing but the x star. Let's imagine this. Okay, it's a new data point. Okay, is actually is lying far from the remaining data points. Remaining training observations. Remaining training observations. What is the remaining training observations? That is nothing but xi, right? So if it is very far from the remaining observations, what is this far? Far is nothing but the distance here. Okay, it's actually at very large distance. For example, here we have the x, right? And here here we have xi. X is nothing but the x star. Okay. Here we have the new data point. New data point, or we can call it as test data point. This is the training data. And in between these two data, in between this single data point and between these rest of the data points, if we have much larger Euclidean distance, Euclidean distance is very large. Sorry, very high actually. If the distance is very high, then what happens? Then then the expression sigma j equal to 1 to p of xj star minus xij whole square will be very large. What happens if this distance, if this is large? Okay. What happens if this is large? Nothing but simple. Our if this is large, what happens? Then k of x star comma xi is equal to exponential of minus gamma sigma j is equal to 1 to p into xj star minus xij whole square. This entire expression value will be very, very small. Why? Because see here, we have the term called exponential, right? So exponential. So if this particular term is large, then this exponential will automatically reduces the entire value. Okay. For example, if this is small, then this entire expression will definitely reduce to some value. Okay. So that's the use of this exponential. Okay. So what happens then? So we can clearly say that xi dash, okay, we can clearly say this xi dash is actually, see, this xi, this particular xi, okay. So this xi is not important in predicting the class for the data point x star. Okay, that means only nearby data points can predict the class for x star. Did you get the point? If you didn't get this particular point, no worries, I'll explain. Why? Because see here, what I'm trying to say is, see, this expression, right? If this expression, that's nothing but if this entire expression is larger, then automatically the entire expression would be very small. Why? Because we have the exponential value. So this will definitely reduce the entire value. So what I'm trying to say is here xi is not actually playing any important role. Okay, this xi is actually not important. Why? Because this is actually not playing any kind of role. Why? Because the entire value of this entire expression would be depending upon the distance between this, right? So this xi is actually not playing any much value. So we can say far away data points are actually not so important in predicting the in classifying the data point. Only nearby data points are actually important in predicting the class for xi. So I can give you a simple example. Like I have a feature space like this. I have some kind of margin like this. I have some kind of margin like this. And here I have some kind of data points like this. Okay. Mm, here I have some kind of data points like this. Here I have some data points like this. Okay, like this. Also here I have some kind of data points like this. See here, now when you compare this entire statement with this particular diagram, we can definitely say that these data points are nothing but the xi. These data points are nothing but the xi, right? And these data points are nothing but the xi. So what I'm trying to say is, if a new data point, let's say, uh, if a new data point has entered, okay, if a new data point has entered, okay, and I want to classify this particular data point, whether it belongs to this category or whether it belongs to this category, I want to say. So what I'm trying to say is, this particular classification of this new data point doesn't depend on the far away data points. Okay, it actually depends on the data points which are actually lying on the hyperplane or actually lying closer to the hyperplane. But it doesn't depend on the data points which are actually far away from the hyperplane. Did you get the point? So that's what it is. If I want to predict this, whether it belongs to this or this category, I will only depends on this particular data point. This why? Because these are actually lying close to the margin, so this would be critical in deciding, in predicting the class of this particular observation. So similarly, in this case also, if I get any okay, if I get any some data point, new data point like this here, and I want to classify that particular data point, whether this data point is belong to this category or this category, I may usually depends upon the data points like this data point, this. Why? Because these are actually lying close to the margin. I won't be depending on these far away data points. That's what I'm trying to say. Okay, only nearby data points matters to me. And now we have completed the kernel section, and now we gonna look for the advantages of the using kernel. What are all the advantages of using kernels? That is the pros of using a kernel. So the first pro is nothing but using this we can minimize. I mean, we can maximize. So the color is actually not visible clearly, so I can change and definitely change. So what are all the things we can do using this kernel? We can increase the feature space using functions, right? What are all the functions? Yeah, the functions may be polynomial functions or interaction functions, etc. Whatever maybe it is. Okay. And the second point would be, it is it's computationally efficient. It's computationally very, very efficient. Why I am saying this? Why? Because see, if we can calculate, see, we calculate k of xi comma xi dash, okay, and this can be done, this can be calculated, this can be calculated without maximizing the feature space also, right? Without maximizing the feature space also, we can calculate the k of xi comma xi dash, okay. This is very important. Why? Because this is so important, because many applications in SVM increases feature space. I mean, what I'm trying to say is, see, I'm trying to say, because in many applications, many applications of SVM, see, I'm writing, this is so important because I'll try to write this entire statement in different line so that it would be clear. This is very important because in many applications of SVM, in many applications of SVM, increased feature space is so large that makes our machine tough to compute. See, for example, if we have only two features, okay, if we only have two features, then it would be easy to compute. Then what if I have some 1 crore kind of features? Okay, maybe this is an impossible feature, but let's say have some kind of 1 crore kind of features. Then the computational power of our machine, of our system, would be very, very slow. Why? Because we can't even compute, we can't even calculate for those 1 crore features, right? So this is actually important. Why? Because here the kernels, the main advantage of the kernels is they won't be using any this kind of particular feature like maximizing the feature space. They won't be using that. Why? Because without using the maximizing feature space, they are actually creating a non-linear decision boundary. This would be very, very important if we want to solve this particular problem computationally efficient. Then this property would be very, very important, right? So, and here I have already explained about the radial kernel, right? So, in radial kernel, feature space is infinite. Feature space is infinite dimensional. So, we can't compute efficiently. See, in the radial kernel, the feature space would be infinite dimensional. That is, there would be having many number of features. So, in that case, we can't even compute this particular. We can't even perform the computations in radial kernel. Radial kernel, right? So, I'm giving some kind of example here. Let's say I have some kind of feature space here. See, this is the example for the radial kernel. Okay. For example, I'm having some kind of data point like this. Okay. I also have some kind of data points okay. Now I also have this data point like this. So this would be one scenario, and I have another scenario where I am having this infinite dimensional space, and also I'm having some data points like this. Okay, and around these data points, I'm having like this. And here I'm having this particular data point here. And here I'm having like this. So I have these kind of data. See here, this is a non-linear scenario. We can't even separate or we can't even classify this particular data using a simple straight line. We can't even do that. Okay. So in this kind of scenarios, we usually use the radial kernel. Okay. See the term radial kernel. So what happens when we do this particular radial kernel? See, I'll tell you. For example, how can we separate using this? So I'll actually compare. Okay, I'll try to give the examples for the comparison between polynomial kernel and regression. I mean radial kernel. Okay, so for this I am trying to solve this particular problem using the radial kernel. So I'm trying to solve this particular problem using radial kernel, and I am trying to solve this particular problem using the polynomial kernel. So I'm saying SVM, that is support vector machine, and I'm also saying radial kernel, polynomial kernel. What are all these things? You maybe have some kind of confusion. See, radial kernel is an approach. Okay, polynomial kernel. Polynomial kernel is an approach. But here SVM is the master. Okay, SVM can use both of the approaches. SVM can use polynomial kernel SVM can also use radial kernel also. Okay. See, SVM is actually using this polynomial kernel to separate this particular data. So how to do that? Let's have a look here. So actually, this is not the case here. So I'll tell you. So okay, this would be the case. So with the help of polynomial kernels, SVM can classify this data as like this. It can classify this like this. Okay. See, did you get that? See, what I'm trying to say is, see, this would be the hyperplane. Okay, this would be the margin on either sides. So this will be one of the margin, and this will be another margin. Okay, and this is a hyperplane, this dark line, and this dotted line is one margin, and this dotted line is another margin. So using polynomial kernel, we can classify the data points like this. So when we are actually using the polynomial kernel, so what would be our d value? D value is nothing but let's say d value is equal to 3. Let's say you can imagine. So no matter whatever maybe the d value is, but it should always be greater than or equal. Should always be greater than 1. Then only we can say that it's a polynomial kernel. Okay. So now we are actually classifying the data using radial kernel. Okay. Actually, SVM is actually classifying the data using the radial kernel. How to do that? Let's see. So see here. Okay. And then like this. Like this. See here, we have got the three nonlinear decision boundaries, right? See, this is one of it, and this is one, and this is one thing, right? So by this we can say that this is a kind of approach with which we can classify the data. Got it? So likewise, we can solve the problems with the radial kernel and with the polynomial kernel also. So this is all about the support vector machines. And we also have one thing left, like applications of the support vector machines. I want to explain that now. So to just look here, this will be our support vector machine things. See here, these are all the things which I have explained. Got it? So now I'll explain you. Now I'll explain what are all the applications of the support vector machines. Got it? So for that purpose, I'm actually importing some kind of images here with which you can understand better. See here. Okay, just see here. Okay, so I want you to explain. I mean, I want to explain this particular application of the SVM. So I'm keeping the heading as application. Application of SVM on hard disease data. Right. So how to understand that? See here. How do you understand this particular image? See, we have already used. See now here. We are actually using two algorithms. That is the support. One is support vector classifier, and the other algorithm is the LDA. Two models actually. Support vector classifier model, and the other one is linear discriminant analysis model. And here we are actually using some support vector classifier. Okay, support vector classifier, and this is the training data. So this is also the train data. Okay, but here we are actually using these two algorithms, but here we are actually using uh, support vector classifier with different values of the SVM. Okay, and now this would be our test data. I'll explain test data, but let me explain this particular train data first. Okay, so if you want to build any kind of model, what do you need? So I want to build this particular model. Here it's actually showing in the above diagram. So how to build that model? Nothing but just you need to calculate you need to estimate the parameters, that is beta naught hat plus beta 1 hat, beta 1 x1, beta 2 hat x2 plus and so on, plus beta p hat xp, right? So we need to calculate this point, and we will specify a cutoff. What is that cutoff? For example, if f hat of x is less than t, okay, if less than t, let's say uh, 0, we can call if let's say t is equal to 0. Okay, if it is less than t, then what can we say? The person has no heart disease. Okay, and what if f hat of x is actually greater than or equal to t? That is nothing but t should be having greater than or equal to 0. Okay, t is less than 0. If this is less than 0, then this person has no disease. And if this is greater than or equal to 0, then we can say the person has heart disease. We can say this. Okay. So usually we do that. So this would be the usual scenario, and by calculating these kind of things, we have already built some kind of model here. See, on the training data I'm explaining. Okay, see this particular this red line is nothing but the support vector classifier model. Okay, this red line is nothing but support vector classifier. Okay, and this blue line is nothing but our LDA, linear discriminant analysis. Okay, here we are actually seeing the the curves of the both false positive rate and the true positive rate. Okay, nothing but the ROC curve. Okay, so this is nothing but the ROC curve. ROC, what is meant by ROC curve? ROC curve is nothing but plotting out false positive rate and the true positive rate here. Okay, so if you plot this, then which model is actually leading here? Just observe the above curve. So actually the red color line is actually leading. Why? Because it's on the top, right? So we can say that SVC, that is support vector classifier, is actually leading. So we can confirm. Support vector classifier is actually leading here. Okay, here. But just look at here. Here also, when you see here, support vector classifier, that is this particular red line, is actually leading in the both the scenarios. See, this is the SVM. This black line is nothing but the SVM. SVM with the gamma equal to 10 to the power of minus 3 value. Okay, and green line, this green line is nothing but SVM with gamma is equal to 10 to the power of minus 2, and this final blue line is nothing but gamma SVM with gamma is equal to 10 to the power of minus 1. So see here, which one is leading? Actually, the blue line here is actually leading in the first place. See, this is in the first place, and then support vector classifier is actually in the same place also. It's actually leading with the first place. So here support vector classifier is actually performing very well on our training data. Okay, on our training data, it's actually performing very well. Got it? And this would be our one minute. Okay, so just remember here the support vector classifier, which is actually leading on the top, is actually performing very well. Here also SVC is actually performing very well, and along with that SVM with gamma equal to 10 to the power of minus 1 is actually performing very well. Okay, just remember that. And now we are actually going to look at test data. So this would be our test data. So what happens? Let's see. See, this is the test data. Okay. So here, when you look at here, what do you observe? Support vector classifier, which is the red line, is actually leading. So it's actually performing very well. So here SVC is leading. Okay, it's actually SVC is leading. So we can conclude that support vector classifier is actually performing very well on train data as well as on the test data. Okay, but when you look at here, support vector classifier is actually performing good, but when you look at the this particular SVM with gamma equal to 10 to the power of minus 1, it's actually leading here. Okay, it's leading. And when you look at this particular green, that is 10 to the power of minus 2, here, it's also performing very well. When you look at this particular black, that is gamma equal to 10 to the power of minus 3, it's actually somewhat having some poor results. Okay, so the first one is actually SVM with gamma equal to 10. Gamma equal to 10 to the power of minus 1 is actually performing very well, but support vector classifier is actually having some drastic change. Okay, so this would be the case. These are all the performance of the individual algorithms. Okay, but we need to compare it. We need to compare that. See, when you compare this, what happens is earlier support vector classifier is actually on the top, right? See here. See, SVC is actually on the top. So it's actually performing very good here. But when you look here, SVC, that is support vector classifier, is actually below. So this is worst here, very worst. Okay. But when you look here, what is this support vector class if this SVM with the gamma equal to 10 to the power of minus 1? Okay, gamma equal to 10 to the power of minus 1 is actually performing gamma is equal to 10 to the power of minus 1 is actually performing very well here. Okay. Oh, sorry. It's actually very worst here. Why? Because see, the curve is actually lying below. See, this is the curve actually lying below. And when you look at here, this particular blue line, which is nothing but the support vector machine with the gamma value 10 to the power of minus 1 is actually performing very well. So we can conclude. So by this we can conclude what we can conclude. Earlier, support vector classifier performed very well on train data. But on test data, it performed very badly. Okay. So by this we can conclude. By this we can say a conclusion, that is a flexible classifier will also produce lower training error and a huge test error. So what does this mean? The meaning of this particular The meaning of this statement is, see, a flexible classifier, that is, it can produce lower training error. Our error should be low, right? So if it produces the lower training and error, that means it's actually performing very well. Okay. So if it is producing the huge test error, that means it's performing very worst, right? So we can our conclusion meaning is, if classifier, a flexible classifier in the sense, a flexible classifier in the sense, any kind of good classifier will actually performs very well on the training data, and also there may be a chance that it can produce worst results on the test data. Okay, so that would be the case. That would be the scenario here. And now, so by this we have already looked for the applications part. Now I'll explain SVM. See, I'll write here SVM with more than two classes. What if we have the greater than two classes? For example, we have the colors. See, for example, we have the colors. What is that color? Let's say I have a color called red. Okay, and I have another called green. I have another color called blue. So this would be the case where we have the classes which are greater than two. That is one class, two class, third class. Okay. So we have three classes here. That is greater than two classes. So how do we fit the SVM algorithm for greater than two classes? Simple. It's nothing but very simple. We can extend. We can extend the same SVM concept to greater than two classes. Greater than two means, I mean, there is no limit how many number of classes do we have. For that, there is no limit. For example, here we have three classes, right? What if we have another colors, like we have infinity number of colors? Okay, for that we have infinity number of colors. That is, for instead of saying greater than two classes, I can say that k classes. K classes is nothing but, when we have k will be used, this term k will be used when we have infinite number of classes. Okay, so we can simply extend the same support vector machine concept for the classes, no matter how, I mean, how many are there, no matter. So for this, in order to solve these kind of many classes problem, we have two approaches. The first approach is one versus one. Second approach is one versus all. Okay, did you understand? So firstly, let me tell you about one versus one. So one versus one. For example, I have the red, blue, green, and how many? Okay, let's say orange. I have these four classes, right? I have these four classes of colors. So how to perform one versus one approach on these four classes? I can say like this. I can say, Okay, so I can say that red versus blue, okay, and red versus green, and red versus orange. So this is my approach for solving the problem which has more than two classes. Okay, this is one versus one. Why? Because see here, I'm actually using only red versus blue, red versus green, red versus orange. Okay, and then now I will use like blue versus red, blue versus green, blue versus orange, right? And now what can I do? I can just simply do like another thing like green. Okay, green versus red, green versus blue, green versus orange. And now here I can do that orange versus red, orange versus blue, orange versus green. So this would be the one versus one approach, right? Why? Because here actually I'm using only one kind of class for one class. See, I'm using this red class versus one class, that is blue, and I'm using the same class for another class, using the same class for another class. Likewise, I'm using for all the classes. So this would be the approach for one versus one. Okay, so here what we can do is here let's say we compare kth class. Okay, we compare kth class as plus one, and we compare kth dash class as minus one. For example, if the data point is actually belonging to this kth class, then we will dedicate this class as positive plus one. If the data point is actually belonging to the kth dash class, then we will dedicate that data point to the minus one. So I will based on any of these classes, sorry, we assign the data point. Don't worry, don't just get confused. I'll explain it later. But just first, let me write this to any class using K2 classifier. Right. See, I'll give you an example. I'll give you an example. If a new data point has come, right? See, we have a new data point like this. Okay. So what we can do is we count how many number of times does this particular data point is actually assigned to each of the K classes. Did you get the point? For example, we will count that if this data point is actually assigned to this red class, or if it is actually assigned to this blue class or orange or green. We will usually count now how many number of times does this particular data point is actually assigning. Okay, then what happens? We will get the count of it, right? We will get the most frequent count. Most frequently occurred count. So by this we can finalize the classification, right? So I can simply tell you the formula for it so that you can easily understand it. See here, I'm explaining the formula. See here, we have a formula called split of data. That is, if we want to classify any data point, we have a formula. That is nothing but, what is the formula? Number of classes. Okay, number of classes into number of classes minus 1 and divide this entire thing divided by 2. Okay, if you do this, then we will get the category, then we will get the classification of a data point, whether that particular data point is belong to red color, or that data point is actually belonging to green or orange or whatever it is, right? So let's try here. See how many colors are there. Here we have red, blue, orange and green. So total four classes, right? So total 4 classes are there. So we have the total 4 class. Okay, into, so how many total number of classes are there? 4. And here we have a new data point. Okay, so it will definitely belong to some kind of class. Okay, so if we minus that in our total classes, though, then how many will be remain? How many we will get? So total of 3, right? So divided by 2. So that is nothing but the 6 here. Okay. So depending upon the count, we can assign that whether it belongs to blue or green or whatever it is. See here, what have we got? See here, we have got the value as 6, right? And what have we got here? See, here we have, how many reds are we having? How many reds are there? 1, 2, 3, another 4, and this is 5, and this is the 6, right? So this is all about the permutations and combinations, right? So we are actually having so many combinations, out of which each class is actually repeating for 6 times. Okay, so this is what it is. 1 versus 1 approach is actually, we will actually perform this kind of approach, 1 versus 1, like this. Based on any of these classes, we assign the data points to any class using this classifier. This would be our formula. Okay, and how to decide? How to decide whether that point is actually belonging to which class? How to decide that? So that will be decided using nothing but we count. Okay, we count how many number of times does the data point occurred to each of our k classes, right? And we decide based on the class for which the data point has occurred frequently. See, I'll explain you in the layman terms. Okay. For example, I have a new data point here. Okay. And here I have some colors like blue, green, orange. Okay. So I'll be counting. For example, if I have a data point, this data point is actually categorized as like this. See, this data point occurred here. Okay. And again, after the classification, this data point is actually occurred here. Okay. And this data point is actually occurred here. And again, after some classification, this data point is actually occurred here. And again, this data point is actually occurred here. This data point is actually occurred here. So this data point is actually occurred here. So likewise, after 6 types of classes, I mean, after dividing this into 6 types of, after allotting this data point for 6 number of times, then what happens is we will count the most of the times for which the data point is actually allotted to a particular class. See, here I have performed some kind of 6 times. Okay, I have performed 6 times. Sorry, this is not there. 1 minute. See, here what happens is, here I have performed 6 times. Why 6 times? Why? Because in our previous formula we got the answer as 6, right? So that means we can form 6 times, I mean 6 kind of combinations. So I have classified this particular data point and allotted some kind of classes to this data point for 6 times. This is the 1 time, 2nd time, 3rd time, 4th time, 5th time, and the 6th time. But for the most of the times, I got the data point which is placed in this orange category. So I will definitely decide that this particular data point is actually belonging to orange category. I will decide like this. Okay. This is the approach, nothing but 1 versus 1 approach. This is the approach of 1 versus 1. Did you get the point? Oh, okay. So this would be the case here. And when it comes to another approach called 1 versus all, I'll explain. So 1 versus all classification. So how can we do that? Very simple, right? So let's say we have blue, green, orange categories. Okay. And we need to categorize this. So how to do that? let's say we have another category red. So how to do that? Very simple. Like I will categorize blue versus green, orange, red. Okay, and then I categorize green versus blue, orange, red, and I categorize red versus blue, green, orange, and I categorize orange versus red, blue, green. So this would be the approach. Okay, so this would be the approach if you want to solve the problem which has multiple classes. So this is nothing but one versus all. Did you get that? So this is the approach here. So what we can do is we can calculate the f of x here. So for this purpose, we usually classify, we usually calculate the f of x. F of x, what is f of x? Beta naught plus beta 1 x1 plus beta 2 x2 plus and so on plus beta p xp. So this would be our equation, and if we get our value, that is f of x. Okay, and if f of x is greater than 1, then we will assign a data point. We can say that x belongs to x is nothing but x star is nothing but a new data point. Okay, x star belongs to kth category. We can say like this, kth class. Okay, and what if f is what if f of x is less than 1? Then what happens? We can say x star belongs to k minus 1th class. What is k minus 1? See here, this GOR are nothing but the k minus 1th class here. Did you get that? But here blue is nothing but the kth class here. Okay, likewise this is the kth class and this is k minus 1. So likewise so on. Got it? So likewise we will use this approach one versus all to classify any new data point as two categories. Like, so this would be the this would be the end of the approaches part. Now here just for this I just want to share some kind of, I just want to explain here one last thing. By this we can conclude our SVM total series. Okay, so here I want to explain relation between SVM and the logistic regression. So what is the relation here involved? I'm going to explain that. So first of all, we everybody knows for any model we have the f of x, that is nothing but the representation of our model, that is beta naught plus beta 1 x1 plus and so on plus beta p xp. Okay, so this would be our value, and we have already seen that uh, what we can do, we usually minimize the error. What kind of error? Error is nothing but here, I'll explain. Beta naught, beta 1, x1, and so on. Sorry, this is beta 1 and this is beta p, and sigma equal to 1 to n, and we need to maximize this particular 0 comma 1 minus yi. If you are actually worrying about this equation, I have already explained it in my part 2 video of SVM. Just please check it out. And plus lambda j is equal to 1 to p to beta j square. So this will be our equation. Okay. Here, what is meant by the lambda here? Lambda is the positive tuning parameter. It's the tuning parameter here. Okay. So lambda is nothing but the tuning parameter. What happens when lambda is large? What happens when lambda is large? That is beta naught, beta 1, and so on, beta p, and so on, beta p will be small. Got it? So lambda is actually controlling these parameters. Okay, if lambda is large, then these will be small. Okay, and also when you watch the part 2 of the SVM video, I have clearly explained that SVC, that is support vector classifier, will allow some data points to be placed on the wrong side of the hyperplane. Those are nothing but the violations. Okay, also violations are allowed. Okay, and also it has some kind of low variance, high bias. Okay, also it has some low variance and high bias. What if lambda is small? If the lambda is small, then what happens? Less violations are allowed. Less violations are allowed, and it will have high variance, low bias. Okay, and that is if lambda is small, then C will be small. Right? Lambda and C are actually directly proportional. If lambda is small, then C will also be small. That's it. So lambda is actually having this thing, j equal to p beta j square. So if you want me to explain this particular thing, this is nothing but the Ritz penalty term. It controls bias variance trade-off. For support vector classifier. Okay. So this has I have already explained this entire thing in the previous class itself. So this is it. So how can you write this particular equation? So you can write this particular equation as loss plus penalty, right? So we can do like this: minimize. We need to minimize this loss plus penalty terms, that is x comma y comma beta plus lambda into p of beta. So we need to minimize this. Here we have the parameters and so on beta p. Okay. So what is this particular L of x comma y comma b? This is nothing but the loss function here. This is nothing but the loss function. What would it actually measures? Okay, it measures the extent to which our model fits the data. Okay, so what is mean by this particular lambda value? I mean, that is this particular p of b. This p of b is nothing but it's a penalty function. It's a penalty function on parameter b, that is beta, on parameter beta. Okay, so and this is controlled by lambda. Lambda is nothing but the tuning parameter. Okay, so this is it. So this particular L of x comma y comma b is nothing but the riz comma lasso. Okay, so this loss function can be written as like L of x comma y comma beta can be written as sigma I is equal to 1 to n yi minus beta naught minus sigma j is equal to 1 to p xij into beta j whole square. So we can write this particular lasso. So this is nothing but the lasso comma rigs. Okay, so this is it. So out of this entire expression, what is mean by this rigs and what is mean by this lasso? So see here, we have written this loss function for lasso and ridge. Okay, and we also need to write this particular penalty function for both lasso and ridge also. So how to do that? So we want to so we need to write the loss function. What is meant by this loss function? sorry, not loss function, the penalty term, that is P of V. P of beta is equal to sigma j is equal to 1 to P beta j square. This is for the lasso. This is for the ridge. Okay. So this is for the ridge. And P of beta is equal to P of beta is equal to sigma j is equal to 1 to P mod beta j. Right. This is for the lasso. So this is for the lasso part. So we have already looked for the lasso and ridge. So how can you write this particular loss function for both the lasso and ridge? And how can you write this particular penalty function for both lasso and ridge? We have already seen. So now okay, so now I will write this loss function of, I'm writing this loss function. See here, now I'm writing, I'll show you how to write the loss function for SVC, that is support vector classifier. So this is, so L of x comma y comma beta is equal to sigma I is equal to 1 to n max of 0 comma 1 minus yi of beta naught plus and so on plus beta p xip. This particular entire equation is also known as the hinge loss. Okay, this entire expression is also known as the hinge loss. Okay, what is meant by this hinge loss? I'll explain. Don't worry. See here, see here. Okay, so we have the two models. Like let's say we have this particular model, and we also have another model like something like this. Okay, so this particular orange line is nothing but the logistic regression. Okay, and this particular white line is nothing but the SVM. So this this orange line is nothing but the loss function. Okay, loss function for logistic regression, and this white line is nothing but the loss function for the SVM. Okay, so okay. So now I will come to this point, but before that I need to explain one important point. I have already said that. See here, whenever we have a hyperplane here and we have some kind of margin here like this, we have some data points here. Okay, so here we have some kind of data points here. But now here we have some other data points here which are lying very far from the hyperplane. So I have already explained you that only the data points which are actually present actually on the margin will are known as the support vectors that impact this marginal hyperplane. Okay, this hyperplane. So now I'll explain the reason for that. Okay, because see here, the loss function is 0 at the data point which are the correct side of the margin for SVC. So what I'm trying to say is these data points are actually important, but not these. Why? Because our loss function, our loss function is actually 0. See here, when you look at this particular white line, see here, it is the value, it is the 0, right? It is actually approaching towards the 0, right? This white line is actually approaching towards the 0. Actually, it has already approached the 0. So we can conclude that loss function is 0. Okay, loss function is 0 for the data points, for the correct data points, for the correct data points. So that is, this white line is actually approaching towards the 0. See here. Okay, so we can conclude loss function for the SVM, that is support vector machine, is actually 0. Why? Because for which, for the correct data points. What are the correct data points? These are the correct data points, right? These are the correct data points because these are actually lying very far from the hyperplane. So these are treated as correct data points. So these data points are not that important. Why? Because here our loss function is already 0. So there is no scope of minimizing the loss function for these correct data points. So these are not important for us. But here the loss function for these data points which are actually lying on the which are actually lying on the margin, these are very important. Why? Because the loss function for these data points is very high. Okay, see here, this particular loss function for this data point is very high. So for that reason, only these points are actually important for us and not the correct data points. Okay, so that's the reason. So due to this particular similarity, what happens is logistic regression and SVM will actually behave in a similar way. It will also give us the similar results, same results. Okay, it will also give us the same results when the classes are actually mixed. Okay, but what if the classes are actually separated, well separated? When I'll explain you, like see here, see here, this is the hyperplane, right? So these are the classes. So these are the classes. So this is the case where the classes are actually well separated. So in this scenario, SVM will give the better results than logistic regression. Okay. SVM will give better results than logistic regression. Okay. But what if the classes are actually mixed? That is, the classes are actually not separated well. See, in this kind of scenario, what happens is logistic regression and SVM will give the same results. Will give same results. Why? Why? Because I have already told the reason. Why? Because the log loss function for the SVM and the log loss function for the logistic regression will almost approaches zero for the correct data points. So for that reason, logistic regression and the SVM will give the same results. Okay, will give almost the similar results. So this is the topic here. So this is the end of the topic here. But I just want to tell two more things now. The one thing is we are actually using SVM, right? See, SVM uses this kernel. Why? Why? Because to maximize the feature space, right? To increase the feature space. To increase this feature space, SVM uses the kernels. Okay. Why to increase the feature space? Why? Because we need some nonlinear boundaries. Nonlinear boundaries. Okay. But is it the only algorithm which is actually using the kernels? No. Why? Because we can also do logistic regression. We also have logistic regression and other classification methods. Other classification methods. Okay, which are actually creating the non-linear boundaries. Okay, so this is not only the case. This is just an option. So we have another option, that is logistic regression also, with which we can also solve the classification problems. Okay, and this is the relation between the SVM and the logistic regression. And also I'll end this video by just by just explaining the one single topic, that is nothing but the SVM for the regression. Can we use SVM for the regression? Yes, we can also use the. See, you know that regression means where we have continuous values, right? Continuous values. So for that we have, if we want to perform SVM for the regression, we have something called There is something called support vector regression. Okay, we have support vector regression. Same like the in linear regression. In linear regression, we use the OLS regression, that is ordinary least squares regression. Ordinary least squares method. This method needs the parameters, that is beta naught and so on, beta p. Okay. Why do we need the parameters? To know the error. Okay, to know the error. To know the sum of squares error. Okay, this sum of squares should be very, very low. This is the condition here in the linear regression. Okay, this is the condition here in the linear regression. But what in the SVR, that is the support vector regression, in support vector regression, it also needs the parameters, that is beta naught, beta 1 and so on, beta p. But this minimizes the different types of loss. Okay, why do we need parameters here? Why do we need parameters here? Because to reduce the some loss, different types of loss. To reduce different types of loss, because here SSE is actually very, very larger. So if SSE is very, very larger, then this would add to higher loss function. So our loss function would be very, very high. So if we want to minimize the loss function, we would need these parameters, and this is nothing but the approach. See, we need these parameters beta naught, beta 1 and so on, beta p, to reduce the different type of losses. Why? Because our SSE would be very, very high. If this is high, then automatically our loss function will also be high. So we need to minimize the loss function. For that, we need parameters. So this is the end of the SVM series, support vector machine. So these are all the concepts. So I can understand this particular video is actually a bit lengthy, not a bit lengthy, but it's almost very, very lengthy. But I'm sure by this you can able to understand the SVM topic in a greater detail. See here, these are all the things I have just explained. Okay. You can just take a screenshot while watching the video. Okay, so this is the end of it. By this I have already I think I have already crossed the 3 hours duration, I think. So yeah, so this is the result of my hard work. If you just like the explanation, then just hit like and share the video with your friends too. See you in the next video. Just subscribe my channel. Good night. Take care. Jai Hind.